Alright, welcome to the third lecture, Deep Learning for Natural Language Processing in Summer Semester 2020. Our topic today is learning in multiplayer perceptrons, and especially we will see the backpropagation algorithm and gradient descent. So what is gradient descent? That's a general optimization technique to optimize functions. That is to find the minimum or maximum of a differentiable function, and we will get to know this technique today. As the second main topic of today's lecture is backpropagation, which is a general technique to determine the gradients of neural networks. And especially we will combine backpropagation with gradient descent. So gradient descent is an optimization technique that requires the gradient, and backpropagation is a method to determine the gradients in multilayer perceptrons and other types of neural networks. And finally, once we have discussed these machine and deep learning techniques, we will come back to natural language processing, and we will discuss language modeling, because language modeling has become one of the core elements of modern NLP. So let's talk about gradient descent first. We consider the general problem of minimizing a function f that takes arguments that lie in R to the n and maps to real numbers, and we want to minimize that function over its domain. And a general technique to do so is called gradient descent. And how does that work? Gradient descent, so it works as follows. It's an iterative algorithm that starts out with some initial guess w. So we initially guess a solution, maybe randomly, or maybe it's an informed guess what the solution could be of the minimizer. So we have a w, which we could also call w0, which is an initial guess of the minimizer. Then we compute the gradient of our function f at our initial guess w. And what is the gradient? The gradient is the vector of first derivatives, right? So we compute the vector of first derivatives of our function, first derivatives and partial derivatives with respect to all of the arguments of the function. So we compute our gradient at the point w, we scale that gradient by a positive constant alpha, and then we subtract this scaled version of the gradient from our current w. So this is a vector, this is a vector, so we all together we obtain a vector, and we make this vector here our new update for w. So this is w prime, and this w prime then takes the role of the previous w, right? And we continue to make such an update as long as some stopping criteria has not been met. Okay, we illustrate gradient descent by way of example. So we go in the we go to the simplest possible case, which is a function whose domain is just a real line, and we consider in particular the function w squared minus f. So the graph of this function is given here, and as you can see from the graph and also from your mathematical intuition, we already know what is the minimum of this function, because before we wanted to minimize. So the minimum is -4, and it's given at the point x0, right? So x equals 0. So when x or w, no matter how you want to call the argument, when x or w is 0, then our function takes the minimum value, which is -4. But now let's assume we do not know this and want to get to this solution by gradient descent. So first we have to compute the gradient. Now in our case, we only have one argument of the function, so the gradient is a vector of size 1, which we can write in a standard notation without any vector notation, and it's given by this value here, 2w, right? If you w squared is 2w, and -4, that cancels. So the gradient is 2w. Let's say we start with an initial guess of w equal to -2, right? We think maybe this could be the minimum. And then we end up here, right? -2 is here, and well, the value of -2 is 0. Then we compute the gradient. The general formula for the gradient is 2w, but at the point -2, the gradient is -4. So now what the gradient tells us is, it tells us the opposite direction of where we have to go, right? Because we go back to the formula, we see that's a gradient scaled by a positive constant, and then we go in the direction of minus the gradient, right? So we have our current direction, and then we add to this direction the negative gradient scaled by alpha. So we go in the opposite direction of to which the gradient points to. The gradient points to the negative side, so we go into the opposite side. So we go to the right, right? And then how far we go to the right depends on our alpha, right? So if alpha is very small, we would end up here, and you see we have already improved. So this is a good thing, we have improved. We could go a little bit further, we could improve more by going further. And if we were very close to 0, that would be the best improvement. If we go even further, it would not be so good as the previous as the previous case. And if we go too far, if our alpha is too big, right, then it becomes dangerous, because in this case you see that we are not optimizing anymore because we go in the wrong direction, right? At this value here, the function value is definitely greater than it was in our initial guess, so this alpha should definitely not be too big. Okay, so as we have seen by way of this illustration, gradient descent, if you pick the alpha too big, it may not even converge, and even if you pick the alpha small enough, it is possible that gradient descent, or it's even very likely that it only gives you a local minimum. So in this case, we have 3 local minima here in our network, and in our error function, so this is some error function. We have 3 local minima. One is a global minimum, so that's the best solution that we could get to. The other one is worse, and the third one is the worst of these 3 local minima. But if we start out here, if our initial guess is here, then gradient descent will lead us to that local minimum, and unfortunately there is nothing that we can do about this. So the only thing that gradient descent is guaranteed to yield is a local minimum, given that the learning rate alpha, so this alpha is also called learning rate in machine learning terminology, given that this learning rate is sufficiently small. So this is the only guarantee that. So there are also other optimization techniques, such as Newton's method or conjugate gradient. Newton's method, what that requires is it requires the second order derivatives. So if the function takes only one argument, so this would just be the simple second derivative, but if it takes many arguments, then we would have to compute d square f over dx dy for all variables x and y. And if we have 1 million variables, then we would have to compute 1 million squared second order derivatives, which is not only a huge matrix in terms of memory, but is also very costly to compute. So while Newton's method may be better and it may converge faster in fewer iterations to the correct solution, it has these immense drawbacks. Conjugate gradient is a technique that works for linear systems, while neural networks are nonlinear systems, and there may still be other approaches out there that can be used for optimization. However, they often require stronger assumptions, such as maybe that the function to be optimized is convex, or they are very costly, like Newton's method, or they require other simplifying assumptions, such as nonlinearity of the system to be optimized. So to conclude this These other approaches have various drawbacks, and at the moment, in the year 2020, the most commonly used optimization technique is still gradient descent, because it is simple. It is guaranteed to find a local minimum if the learning rate, if this alpha is sufficiently small, and it is it is one of the cheapest methods, or plausibly the cheapest method out there, that one can think of. So at the moment, this is still state of the art and used in almost all papers in applied deep learning. Okay, let's go from standard gradient descent for applied to general functions. Let's go to our special case of optimizing machine learning functions, and especially optimizing the error function of a neural network. Okay, so what is the setup that we are facing? First, the setup that we're facing is that we have data xi, ti. What are these xi, ti's? Well, xi are the inputs, ti's are the true labels. So this could be a real number, or it could also be a vector. So each instance, or each input xi has some label ti. So the second thing that we have is a loss function. What does this loss function do? It compares two objects, and the first one is the prediction of our machine learning algorithm. In our case, this would be a deep neural network, and it compares that to the true label, right? So we have the data, we have the error or loss function. And then what objective do we want to minimize? Before we saw how can we minimize an arbitrary function f, and how does this function f look like in our case? Well, in our case, a very plausible structure of this function f to be minimized would be the following. It could be, or it would be, and it is, the sum over all instances in our data. So we sum over all I, and then we sum up the loss for each instance. So for each instance we get a little loss, and we sum up these losses. How do these losses look like? Well, we compare the true label for the instance I with our network prediction. What is our network prediction, or how does that look like? Well, it takes the input xi, and it takes its parameterization w, right? So this is the network prediction. And so from this network prediction, compared to the true label, we get a loss, and we sum up over all of the losses. And now we want to minimize that over all possible parameterizations of the network. So the goal is to find network parameters w, and this w now stands for all of the network parameters. So this is all the weight matrices, all the bias terms, right? So we want to minimize over the parameters. We want to find those parameters that have the property that they have a small loss to the true labels for all of the instances, where the small loss is where the definition of loss is given by the loss function L. Okay, and then batch learning, what people call batch learning, is simply applying gradient descent to this objective function here, right? So it's just like gradient descent combined with this objective function, and the only thing, and the solution is given down here, and the only thing that we have modified in this version is that we know from our mathematical background that the gradient of the sum is the sum of the gradients, so we can pull the gradient into the sum operation. Now there's another technique which is called online learning, and this makes a modification which is as follows. So first we have the same setup as before. We have the same goal of minimizing our same objective function, but with online learning we make an approximation, and this approximation is we compute the gradient of the loss function at one particular point. We draw one point from our data set randomly, and we compute the gradient at that point, right? And we do not sum over the gradients of the loss function with respect to all of the other points. We just consider this one point. So that is the modification called online learning. So we do it first for one randomly drawn point and another randomly drawn point except for the first one, and iteratively until we have seen all of the endpoints in our data set. Now, what is the advantage of doing it in the second way? Well, the advantage is that we make updates much quicker. So in the first case, we have to compute the gradient of the loss function at all of those points, and this takes a lot of time if our data set is very large. So we only make an update to our weight parameters after we have computed all of that, and that may take a lot of time. The advantage here is we don't have to compute the gradient at all points, so we make updates much quicker, right? We immediately make an update, and what usually comes out in practice is that here we have already found a good solution before we have even started to update anything in this version, right? So doing online learning may lead us faster to a good solution. And also another empirical advantage is that sometimes if we do online learning, one observes in practice that it sometimes leads to better solutions, maybe to solutions that generalize better, right? But this is more an empirical finding, which is absolutely no guarantee for your particular data set. And also to mention is that there is something called mini batch learning, which is a very popular term that you will encounter in many papers. And this is just an intermediate solution between batch and online learning. So instead of choosing one point randomly, we choose k points, right? So we take a generalized form. We choose k out of the n points randomly, compute the loss function gradients, and update, right? And this mini batch learning with k bigger than 1 is a standard scenario in optimization of deep learning. However, it is unclear how to choose k, right? So smaller k's, maybe, as I've said, if you use k equals 1, maybe they are empirically better. Larger k's are maybe better if you have multiple machines and can do parallelization, right? So in general, what you can do if you have your particular optimization problem, your NLP problem, then you would make k a hyperparameter. You could, for example, try out k equals 1, k equals 5, k equals 10, k equals 50, 100, etc. Right? So you choose different k's, and on the development set, you check which one of them performs best. And another important terminology is that this mini batch learning is also known as stochastic gradient descent, because we randomly draw these k points, right? That's the stochastic part, and it's the abbreviation is SGD. Okay, what is beyond gradient descent? Beyond gradient descent, we might look into, or we very briefly touch upon three extensions and adaptations. So the first one is we can adapt the learning rate alpha over time. So we have this learning rate alpha in gradient descent and its stochastic gradient descent that we have fixed to some number, but we could vary it either over time as iterations go by, or depending on the curvature of the error function, right? A second thing to do is we can include a regularization term down here. I will talk about this in the next slide. And the third option, among many other options, is to include momentum. And there what we do is when we update at one time point, we calculate the gradient, and when we update our weights based on that gradient. however, the current gradient may be due to an unlucky drawn point. It may from our data set. So we draw an unlucky drawn point from our data set, and maybe at this point, which is maybe an outlier, maybe it's um, maybe it's falsely classified, our gradient could point in the wrong direction, right? And to avoid such little errors, we could smooth our current gradient with a past gradient. So we store the previous gradient, so the previous derivative and the one before, and we smooth the current gradient with the past gradients. So this is the idea if we are going overall in the correct direction, but at one point make a small error, then this small error may cancel out and may be smoothed by the previous correct, in general correct directions that we are taking. So what is the modification of the learning rate? Yeah, well, as we have seen, if the learning rate has to be small enough to guarantee that we converge to a local minimum, but if it is very, very small, it will take a very long time until we reach the local minimum. In contrast, if we have a very high learning rate, we may not converge at all, as we have seen. So we need to find something in between. We shouldn't go too slow, because otherwise it takes too long, and we shouldn't go too far, to have too large learning rate, because otherwise we may not converge at all. So what we could do, for example, we could get an estimate of the error surface. If the error surface is very steep, we should choose a small learning rate in order not to miss our local minimum. If on the contrast it's very flat, our error surface, we could take a very big learning rate, right, so that we advance quickly. And there may be other solutions how to optimally change the learning rate depending on error surface or maybe iteration time. Another very important thing is regularization, and the regularization idea is that you add something to your optimization term, and this something is a regularization term as a function of the parameters, and you scale that by a constant gamma, which is non-negative. And what is done in practice is this regularization term is usually taken to be L2 regularization, which is the norm squared, or L1 regularization, which is the sum of the absolute values of the inputs to R. And what is the idea behind that? The motivation is Occam's razor, and the idea is so that's Occam was a philosopher, I think, from the 12th or 14th century, who proclaimed that if you have two solutions, choose the simpler ones, right? Choose the simpler one. And this is, by the way, just as an aside, this is what all mathematics is based about. So like true mathematics. So if you have a theorem of a proof of a theorem that takes 2 lines, and another person has a proof of a theorem that takes 10 pages, then every mathematician would prefer the proof that has just 2 lines. But more generally, or more a little bit outside of mathematics, what is the motivation of Occam's razor to choose simpler solutions in a machine learning context? Well, imagine that you have found a solution to your optimization problem, and the solution, the weight vector, the vector of all weights, is very high dimensional, let's say 10 million. So you have found a 10-dimensional vector, and assume that all the entries in this vector are very large in scale. So they are big numbers that have a big magnitude, a big absolute value. And you have found a second solution that is performing almost as good or just as well, or maybe even slightly better. And this only uses 2 of the parameter and sets all of the rest to 0, right? And this setting to 0 is given by this constraint here, because we want to minimize here, and minimizing here would be well, if you set everything to 0, that would be the minimum achievable in both of these regularization forms, right? Setting everything to 0 would be the best option. So, but if you can find a solution that uses just 2 parameters, then obviously that's a very simple solution that can solve the problem, and it has intuitively better chance of generalizing to unseen data points. At least that is what our intuition is. And why this could be is illustrated by this next picture here. So in this case, we're in, let's assume we have such data points given by the red ones here, where for each x we have a corresponding label y, and the x is just a real number. And these are our data points that we have in the data. Now we have two solutions. Let's say these are two polynomials. One is a very high degree polynomial, and one is a very low degree polynomial. So the green is low degree polynomial, the blue is a high degree polynomial. Now we have these two solutions, and they perfectly fit the data. As you can see here, both has zero error on the red data point. So this is our data, they have zero error, but they make very different predictions on points that are not in the data. So for example, one property of the green curve is that if you go in the middle of two points, so here you have a point, here you have a point, if you go in the middle on the x-axis, then the prediction is roughly also on the middle and the y-axis, right? So this is always the case. While the blue curve here makes very random predictions, so to speak, for in-between values, right? So it goes very chaotically up and down. So we would expect that, intuitively would expect that the blue curve is a much worse, has much worse generalization capabilities for points that are not in the data set, while the green curve is a much smoother and more accurate generalization and extension and extrapolation of the data points. And the green curve, if that would be a lower dimension, if that would be a lower degree polynomial, it would be given by setting terms for the higher degrees in the polynomial to zero. So it would have, it would use less capacity of the model. It would use less parameters. And this is exactly what is obtained by this regularization term. We try to cancel those parameters that are not really needed. We try to set them to zero if they are not really needed to solve the problem. And beyond all of this, beyond gradient descent and its extensions that we have seen, like including regularization, learning rate, this we would still all be in the context of gradient descent. There are other optimizers. So these things are called optimizers that have been developed in the last couple of years. And all of these optimizers that have been developed in an effort to improve upon gradient descent, but still not go to the complexity of a second order method like Newton's method, right? And these optimizers are called RMS probe, ADA-CRAD, ADA-delta, ADA-norm, ADA-NADAM, etc. And they are standardly given in all of these deep learning packages that you will be using in our class, such as TensorFlow, Keras, etc., PyTorch. They are given there, you can try them out. You can make them a hyperparameter and see which one of them leads to a better solution for you than stochastic gradient descent. And I cannot give you any empirical guarantee. There have been a couple of contradictory results in the last couple of years. So some people have said, these methods train faster, but maybe the solution found is not as good, maybe not as good as generalizable as stochastic gradient descent. But in general, for any particular problem that you are trying out, there is no guarantee. I would just recommend to you to try them out and treat them as hyperparameter and see which one of them works best for you. And I would also recommend to you to always use regularization so that you have a better generalization of your model to test data which are not given in your training data set. So for regularization, what you will often observe is that you have worse performance on the training data set, but then afterwards you have better performance on new unseen test data. All right, let's do a recap of deep neural network terminology. As you know from lectures 1 and 2, we have inputs and outputs in a neural network, and of course. In the first lecture we started out with a perceptron that had only one output unit. Then we can generalize that to multiple output unit. Would still call that a perceptron. Typical case is our outputs, our inputs in NLP. Maybe a text goes in. How does that go in? Well, we have to vectorize that text somehow. That's the input to our network. And then our outputs could be one of M classes. For example, we could have 3 classes, positive, negative, neutral, and we could code them as such one-hot vectors, where exactly 1, 1 is activated per class. So these output units, they all have activation functions, and each output unit is connected with all the inputs by a weight vector, and we have a weight vector exactly for each output unit. In this case there are 3, and the mathematical operation that we do is we take a dot product, the input times the weight vector in each case, and then we apply the activation function. So this is what we're doing here. We apply the activation function, and then we can these individual weight vectors, we can form a matrix from them, W, big W, capital W, and this W lies in R to the n times m, where n is the dimensionality of the input and m is the dimensionality of the output, the number of output units. And the input vector lies in we consider that to be a row vector of size 1 times n. And then if we go in matrix notation, we could do the calculation as now also, I think we also changed that here to all of the output units have the same activation function. So how we can abbreviate that mathematically is we take the linear product x times the matrix, a vector times a matrix. We apply the activation function. So this is a vector. We apply the activation function element-wise, and we take the first element of this vector, the second and the third, and this will be the output of the first, second, and third output unit respectively. So here you see it all together in one matrix, in one slide. We have the weight matrix, we have the activation functions, we have the input vector, the output unit calculates pre-activation and then applies output non-linearities on top of the pre-activations. So if we change to one activation function to the same activation function for each output unit, then the formula abbreviates accordingly. So this was a perceptron. Then we go to a multi-layer perceptron where we have multiple hidden layers, and maybe each hidden layer has a different activation function, maybe or maybe not. And then the math behind that is pretty similar. The MLP is a function, a mathematical function that maps from R to the n to R to the m. It has parameter matrices W1 to WH if there are capital H hidden layers, capital H hidden layers. Then we have H weight matrices and maybe H different nonlinearities. And what is being computed is we compute the pre-activation in layer 1. We compute a pre-activation that is given by the input times weight matrix 1. We get a pre-activation. Then we get the activation in layer 1 by applying the nonlinearity. And then the pre-activation in layer 2 is given by taking this pre-activation, multiplying it by W2. That's the second layer weight matrix. We get another pre-activation, and we do so until we end in the final layer, and we get the activation of our neural network in the final layer. And of course, we have these bias terms also, these bias weights that we should always keep in mind, but we usually drop for ease of notation. So the question is, so this is the setup of a deep neural network. Why do we need the hidden layers at all? First, they can be useful in learning some intermediate representation of the data. So this could help learning, and it can make learning much faster. So having these hidden layers can make learning faster and can find better solutions maybe. While in theory, just one hidden layer suffices. So there's a theorem that if you have a single hidden layer, that is in principle sufficient. But in practice, having multiple of them can make life easier. While if you have no hidden layer, so if you have only the perceptron, then we know this is extremely limited. It cannot even learn the XOR function. While in contrast, the MLP with one hidden layer is a universal approximator, and there are theorems on that, so it can approximate any continuous function. Okay, so this is our setup, and with that we start into our next chapter, which is called backpropagation.